When we describe motion, there are three basic variables that we address. These variables are distance, speed or velocity, and acceleration. Let's discuss each of these three variables individually. To start off, let's talk about distance. Anytime we discuss motion, we need a reference point, a point to compare all measurements. This reference point is something we refer to as position. Anytime we have a change in position, then we can take the difference between those 2 points and we call that distance. So let's say we have a point here. We're going to call that point D sub I. The I indicates initial and the D indicates position. So this is our starting point or our reference point. Then we'll move to some other point off here to the right. We're going to call that DF, meaning D meaning position, F meaning final. Then we can actually measure the distance between these 2 points, and that distance is simply the final position minus the initial position. In physics, we often use this symbol to indicate a change in. This is a difference. This little blue triangle here is the Greek letter delta and always indicates change in or difference between. We always calculate this as the final measurement minus the initial measurement. If you notice in our example that we did here, that is exactly what we did. We took our final position minus our initial position. So this is, another way to write this distance is merely the change in position, delta D, is equal to final position minus initial position, or distance is equal to final minus initial position. The second variable that we address in motion is speed. Another term more commonly used for speed in physics is velocity. So we represent speed and velocity with the variable lowercase v. Speed and velocity are defined as the ratio between distance and time. And so we can calculate velocity as so, distance over the time elapsed, or v is equal to delta d divided by t. So let's do an example now where we take our definition of velocity and actually calculate the velocity of a car traveling over time. Let's take this example. Let's say you are watching a car, and when it hits the 50-kilometer marker, you start the clock. Once it hits the 150-kilometer marker, you stop the clock, and you find that a total of 2 hours has passed. Well, let's figure out the actual velocity of this car. Recall that our definition of velocity is that velocity is the distance over the time. Now this distance, recall, is just a change in, which means final position minus initial position divided by our time. Okay. So in our calculation, let's put in some real numbers. Our final position is 150 kilometers. Our initial position was 50 kilometers. And the total time it took was 2 hours. Okay. Now it's just pretty simple math. Take the top first, do that difference. That gives us a difference of 100 kilometers over 2 hours. 100 divided by 2 would be 50 kilometers per hour. You might see this written more like 50 kph, kilometers per hour. Now, hopefully this was pretty intuitive, because as we can see here, already illustrated in the figure, started at 50 kilometers, went to 100 kilometers, that's a difference of 50 kilometers, it took 1 hour, so we went 50 kilometers per hour. Same for the second half. Now, the difference between velocity and speed is that even though they both measure distance over time, velocity also describes direction. So a velocity of 70 miles an hour to the north is not necessarily the same as 70 miles an hour to the east. but in both cases, the speed is 70 miles an hour independent of direction. So take this example over here on the in this figure. On the top left, you have a car moving 30 kilometers an hour to the east, and on the bottom you have a car moving 60 kilometers per hour to the east. So they have the same direction, but different speeds. Now, if you look at the one on the right, it's also moving 60 kilometers an hour, but it's moving to the northwest. So on the left, you have different velocities and different speeds. The two on the left. These two cars have different speeds and different velocities. But these two cars, they have the same speed, but since the direction is different, the velocity is also different. It is important here to note that speed is rarely constant. When you're driving along in a car, the speed is always changing. So in physics, we usually don't talk about speed as a constant. Rather, we talk about average speed, which we indicate by putting a bar over the letter V. Now let's divert here for a minute. If you recall from your algebra class, we can look at a graph and write an equation for the line on this graph. Looking at a straight line, we can write the equation as y equals mx plus b. But now let's replace the y-axis with position and the x-axis with time. Doing this, we can change the variables in our equation. Y becomes final distance, and your b, your y-intercept, will be your initial distance. In other words, your position at time 0. So our equation now becomes final distance is equal to mt plus initial distance. The trick here now is to find out what is the slope. Recall that the slope is rise over run. So in this case, the rise would be the distance, delta d, and the run will be your time t. Now recall that distance, delta t the ratio delta d over t, distance over time, that's just our definition of velocity. So the slope of this graph is merely velocity. And so we can write our equation as final distance is equal to velocity times time plus the initial distance. So here's a very good physics application of a basic algebra principle. The last term we need to address in motion is acceleration, which is defined as the rate of change in speed, and we indicate this with the lowercase a. Just like speed was the ratio between distance and time, acceleration is the ratio between speed and time, or the change in velocity over time. Basically, acceleration is a measure of any change in motion. When we indicate variables, this is what it would be. Acceleration A is equal to delta V, or change in velocity over the time t. And of course, delta V is just final minus initial. So acceleration is a measure of any change in motion. Now, it's important that we distinguish this, saying acceleration is the change in velocity over time, because when we have a change in motion, this could mean it's either a change in speed or a change in direction. Here in the top, we have a car going 30 kilometers an hour and then accelerates or speeds up to 60 kilometers an hour. On the right, we have a car that's going 60 kilometers an hour, but then slows down to 30 kilometers an hour. In both of these cases, we have an acceleration dealing just with the speed. But in this case down here at the bottom, we have a car that is traveling 30 kilometers an hour and maintains that same speed, but reverses direction. In this case, there's no change in speed, but there is still an acceleration because the direction has changed. Now in this final figure down here, we have both a change in speed and a change in direction. Here's a common example of acceleration. Perhaps you've heard of the phrase 0 to 60 in 10 seconds. Very well known when it comes to car racing, to acceleration of cars. Well, here's what this phrase really is nothing more than a statement of acceleration. Let me show you what I mean. 0 to 60, we're talking speeds from 0 miles an hour to 60 miles an hour. So that tells us our initial velocity is 0 miles an hour, and our final velocity is 60 miles an hour. And how quickly does that happen? Well, 10 seconds, that's obviously a statement of time. Okay. Now, how do we calculate acceleration? Recall that acceleration is nothing more than the change in velocity over time, and change in, as before, indicates final minus initial. Okay, so our acceleration then is going to be the final 60 miles per hour minus the initial 0 miles per hour divided by the time, 10 seconds. Of course, 60 minus 0 is nothing but 60. Divided by the time of 10 seconds, that means you're accelerating at a rate of 6 miles per hour per second. And so when we have the statement of 0 to 60 in 10 seconds, all we're saying is that it's accelerating by 6 miles per hour every second. Just as with speed, we can look at a graph which indicates acceleration. If we take our graph of velocity versus time, then we can take our simple slope equation, y equals mx plus b, and do the same thing we did before. Our y becomes our velocity at any time, or our final velocity. Our y-intercept would be our initial velocity, the velocity at time 0, and our x variable is time t. Just as before, we found that the rise over run is our slope, but the rise is going to be our change in velocity, and the x, our run, will be our change in time. Change in velocity over time is our definition of acceleration, so we substitute that in for our slope. Slope is going to be acceleration, and we have ourselves another equation. The final velocity is going to equal the acceleration times time plus initial velocity.